Thank you. So before I begin, there is an exercise for everybody. So which theorem of Emmanuel is this an illustration? So I will not give the answer. So that's an exercise. I'm not sure, you know. So I'm particularly happy to be here to celebrate Emmanuel's 60th birthday for 3 reasons. The first reason is that I knew at least one of his results before I knew him, and this result is illustrated there. So this means it's not a new... And the second reason is that we are colleagues in Orsay, and we are not in the same team, but we used to discuss together, not very often, but kind of regularly. And it's always at Wednesday noon. So it's okay today. And the third reason is, you will see it in the lecture, I have to thank him for some insight in mathematics that you will see in the lecture. So the topic is convolution and square in Abelian groups. It's a completely elementary topic. So the topic is explained there in this blue line. So you just deal with a finite Abelian group of, so I make some assumption on this finite Abelian group that its order is odd. And I want to understand the function on this group for which a square here is proportional to the convolution square. Here you see this sum for y in G of f of x plus y, f of x minus y by a small change of variable is just the convolution of f with itself at the point 2x. So I'm writing f convolution with f at 2x here is proportional to f of x squared. And in case I have such a couple lambda f, I will say that lambda is a critical value on the group, and the corresponding function, I will say it is a lambda critical function on G. And since this looks too general for me, I will most of the time focus on the case where G is a cyclic group. And I will say that lambda is D-critical. So you have to catch the definition, because I will spend the whole lecture on this precise definition. And in fact, I did some computer experiment on this. I behave like physicists, like doing doing experiments, seeing something, and then when you see something, you want to explain it. So I will tell you more. So let's first give very easy example of such functions. So I have written again the equation above, which says that lambda is D-critical. And if, for instance, you take a Gaussian function, so take a dth root of unity, and f of x, you raise it to x squared. So that's a Gaussian function. You plug this function inside this equation. You see that the double product simplifies. And so it's a solution of this equation. And the scalar that occurs is just the Gauss sum, and which has been computed by Gauss. And it's equal to square root of d, when d is equal to 1 mod 4, and to I square root of d, when d is equal to 3 mod 4. OK, that's the first example. Nice nice example of D critical value. You can do something slightly different. You can take a character of the multiplicative group extended by 0. And when the square of this character is not trivial, in fact, it's a solution of this equation. Let's check it, say, at a point which is invertible. So when you plug this multiplicative, so k is a character, so key of xy is key of x, key of y. And so when you plug it here, you see that you do a change of variable. Y is equal to x times z. And so then you see that it's a solution of this equation, and you have a coefficient, with a proportionality constant, lambda, which is given by this sum, which is just in a hidden way, but not that hidden, just a Jacobi sum. And one knows that, so one are happy to have this critical value, and one can remark that these Jacobi sum have absolute value square root of D. Like they might be complicated algebraic number, but they have absolute value square root of D.
Do you take a primitive character? Because sometimes the character factorizes to Z mod D prime square. D prime. And then you have to have a good property, maybe you need to make it not zero for prime to D prime, but I'm not sure about it.
I see what you are referring to here. With this, it works. Like just to take multiplicative character of the multiplicative group. You assume that chi square is not 1 on this multiplicative group, and you extend it by 0, and then you have a solution of this equation with this lambda. You just check. Easier example is maybe we can try to find f to be constant, or maybe not completely constant, but a constant outside 0. So for instance, if f is completely constant, then f is 1, then for sure it's a solution of this equation, but with lambda is equal to d. So you get this first value, lambda equal d. You can take for f the Dirac mass at 0. So then if it satisfies this equation, and the value will be lambda is equal to 1. And but you can try two values, alpha at 0 and beta somewhere else. And you find a solution, which is this, okay, d minus 3, which is a real quadratic number when d is at least 11. So then the question I want to ask is, are there other critical values? And so I did, as I first, before showing to you the computer experiments, let me just tell you what can be said on these critical values. So it's very easy to check the following. So what I call a proposition 0, that they satisfies 4 conditions. If you have a critical value, you see its absolute value will be bounded by d. Because just check this equation here at the point x where f has maximum absolute value. So then you apply it and you get that lambda is bounded in absolute value with d. So this is easy. And another easy thing is that d over lambda is also a critical value, because you can replace, if you have a solution f, you can replace f by its Fourier transform. And the square becomes convolution, and the convolution becomes square. So you get the same equation, but with d over lambda. That's nice. Another easy remark is that if lambda is a critical value, the Galois conjugate are critical value because the equation has integral coefficient. And the last one is nice also, is that lambda minus 1 over 2 is an algebraic integer. And this will be important in the rest of the talk. So let me give you the proof why it's an algebraic integer. Okay? How do you check something is an algebraic integer? You take ultrametric norm and you prove they are at most 1. So you do the same proof, exactly the same proof as lambda bounded by d, but instead of plugging here the Archimedean norm, you take ultrametric norm. And so you get that lambda in absolute value has to be bounded by this ultrametric absolute value bounded by 1 for every ultrametric absolute value. So this proves that lambda is an algebraic integer. But then you look a little bit at this equation. These terms here, they occur 2 by 2. So, and there is one term here which is f of x squared that you put on the right-hand side. So you get lambda minus 1. And those terms are 2 by 2. So this is why lambda minus 1 over 2 also is an algebraic integer. So this is a nice piece of information on the critical value. And a corollary of the first fact that it is bounded is that, in fact, you just have finitely many critical values. And why is it a corollary? It's a corollary because the set of critical value is a constructible set. It's obtained by elimination. So, and a constructible set which is bounded has to be finite. Okay, so now we know a lot about these values. And what happens also is that, in fact, even if there are only finitely many critical values, most of the time there are infinitely many critical functions. So you can think of lambda as a kind of generalization of eigenvalue and eigenvectors. So there are only finitely many eigenvalues, but sometimes there are multiplicities, and you have a higher dimensional space of eigenvectors.
Is there an actual linearization of the problem that this point of view could be formally?
No, it's just an analogy. No. I mean, no. Thank you for asking. So let me show you the computer experiment I did, and which was the beginning of my interest into this this topic. Let me show you for d equal 11. Okay, so the list, the computer is able to give you the list of all the critical value for 11, 13, 15, 17, 19, but okay, then you are dead. But for 11, let me show you what is the list. So you get the one we have already seen, 1 corresponding to the Dirac mass, 11 corresponding to the constant function, 4 plus square root of 5 corresponding to functions which are constant outside 0, and I square root of 11 corresponding to the Gaussian function. But the computer gives you also these values. 2 plus I square root of 7. 2 square root of 2 plus I square root of 3. Wow. Wow. Where do they come from? So, and also another nice, which is 1 plus square root of 5 plus I square root of 5 minus 2 square root of 5. Where do they come from? So really, I started with this problem, and I did not expect any strong mathematics to enter into it. But right now, the only way I am able to explain these values, and it will be the aim of this talk, is that you need Abelian varieties with complex multiplication, and theta functions on torsion points, and the modularity of this theta function as a function on the Siegel upper half space to explain exactly these values.
Yes.
The properties you listed on the previous slides, they were true for any groups of size D, right? Not only Z mod D.
Yes. This is what I wrote. Yeah, exactly.
Okay.
Yeah.
And how does these physical values behave to take product of?
I mean, if lambda 1 is D1 critical, if lambda 2 is or if lambda 1 is critical on G1, if lambda 2 is critical on G2, then lambda 1, lambda 2 is critical on G1, G2. But you have much more critical function on the product G1, G2 than just the product. Yeah.
Thank you.
And so, just out of curiosity, then, so what led you to study this question?
Sorry?
What led you to study this question? Because it was an accident that these things are coming. So.
I was trying to I was focusing on a conjecture that I found too difficult, and so I tried to find similar problems that I mean, I was doing computer experiment on this more complicated problem, which I call the equiangular dream. So it's this problem is known as the sixth problem of the Zauner conjecture. Maybe you know about it. So I have written a lecture note on it that I call the equiangular dream. So I present this problem, and but on this general question I don't know, so I focus on this. Okay, but for me now, this is interesting in its own. I mean, because you have this very elementary, and you will see this mathematics entering, and you see in this what the computer gives you. It gives you I square root of 11, and it gives you square root of 8 plus I square, so square root of 4 plus I square root of 7, you see? 4 plus 7 is 11. Here 8 plus 3 is 11. So you see you get square root of A plus I square root of B when A plus B is D, okay? But not all AB occur. You go 4 by 4, okay? So there is some congruence condition. And so this is very elementary to say it, but you will really explain this. This is the aim of my talk, because of the properties of the theta function. The theta function have a modular property, but not for all the group SPN. You have to go to finite index subgroup, the so-called Igusa subgroup, and this will explain exactly this congruence condition. And this is why I like this topic. Yeah. So forget about the other one. And so now let me write precisely just what I told you. So these example, you can put them in a general family. Each time you are able to write your odd integer, D is odd, I recall, on the form A plus B with A and B positive integer, with some congruence, wow, I'm too efficient. With some congruence condition on A mod 4, and this congruence condition tells you are going 4 by 4, okay, and starting from the Gauss sum. If D is equal to 1 mod 4, you start from square root of D. If D is equal to 3 mod 4, you start from I square root of D, and then you go 4 by 4. And all the square root of A plus I square root of B here will be D critical. And I will be able to explain this only by using elliptic curves. And then the computer also gave me this example for small value of A and B. Like if you write D is A plus B plus C, 3 positive integer with a positive discriminant, and with some congruence condition, mod 4, like A, B, and C being equal to 1 mod 4, then you do this, you compute this one, square root of A plus square root of C plus I square root of B minus 2 square root of AC is D critical, okay? And if you are in the case where A, B, C are not equal to 1 mod 4 but equal to 3 mod 4, it's almost the same number you get, almost the same algebraic number, but it's multiplied by square root of -1. Okay? And on the one hand, I explain this congruence condition because I know that lambda -1 over 2 has to be algebraic integer. So for this forces this congruence condition when if you want a solution of the form square root of a plus I square root of b. So you are forced to have this, and as I told you, the explanation, I will give this explanation why this one, so the aim of this talk is to explain why these values are critical. Okay. So I need to go to explain what's the general construction of critical value using Abelian varieties. So I know in the previous talks you did not even define variation of mixed Hawk structure, but here I will define Abelian variety. And so what's an Abelian variety? A principally polarized Abelian variety. It's a quotient of Cn over lambda, where lambda is a complex torus. But we need this to be a projective variety, so there is some condition due to Riemann, which says that there exists some positive Hermitian form on Cn, such that the imaginary part, which is a symplectic form on Cn, omega, is integral on the lattice lambda. And principally means that the volume form defined by omega on the torus is in fact of volume 1. So this is what it is. And I will need also the Q algebra of Q endomorphism of my Abelian variety, which correspond to the linear transformation, complex linear transformation of Cn, which may not preserve exactly the lattice, okay, but they preserve the lattice up to commensurability. So they send the lambda q to lambda q. And so it's very well known, but I recall it for the few people, maybe younger, which may not know this. Such a Q endomorphism has two aspects. You can either see it as a complex n cross n matrix, because it's an endomorphism of Cn, or you can see it as an endomorphism of this Q vector space, which has rank 2n. So it's also a 2n cross 2n matrices with rational coefficient. And these 2n cross 2n matrices, I give it notation, h nu, I'll call it the holonomy. And there is a remark that nu is unitary, this endomorphism of Cn is unitary for this Hermitian form, if and only if this holonomy, this 2n cross 2n matrix with rational coefficient, is a symplectic for omega. So it's a well-known basic fact. And those are exactly the notation I need to give you the general theorem to construct not all, but some critical values, which is the next slide. And this is the main theorem of the talk. And I will give kind of three versions of this theorem, which are not exactly equivalent, but kind of variation. But this is the most general one. So each time you have a principally polarized Abelian variety, if on it you have a unitary Q endomorphism, this means that this nu will not preserve the lattice lambda, but it will commensurate it. So lambda intersection nu lambda will have finite index in lambda. So you can construct this finite Abelian group G nu, which is lambda over lambda intersection nu lambda, and which has some cardinality. I call it d nu. And then the theorem is under some star assumption, which is a congruence mod 2 assumption that I will explain. You can construct the following algebraic number, which will be critical on this group G nu. So this lambda is a product of three things. The first thing, kappa, is some fourth root of unity that I have trouble to detect, whether it's 1, I, or minus I. So usually you can easily detect it up to sign, because you use the fact that you know that lambda minus 1 over 2 is an algebraic integer. But the sign is really complicated, and okay, at least I had trouble with it. And the absolute value is the square root of the cardinality of G. And there is the part of modulus 1, which is just the determinant of this unitary operator in Cn. Yeah. As a complex matrix, the determinant in Cn of nu, you take the square root. Okay, so this is the theorem. Okay. And what is the assumption star? Maybe, sorry. So you take your unitary matrix, you take its holonomy, so it's a symplectic matrix in a symplectic basis of your lattice lambda, which has rational coefficient because it doesn't preserve lambda. It preserves lambda only modulo commensurability. So you write it as block matrices, alpha, beta, gamma, delta. Those are n times n block matrices with rational coefficient. And you have the congruence condition that what am I doing? Sorry. H nu, this matrix has to be equal to 1 mod 2, and the diagonal coefficient of beta and gamma have to be equal to 0 mod 4. And this is a very well-known condition in the theory of Abelian varieties. And I will say why later. So here I have to say what I mean because I'm writing congruence condition for rational number. So a rational number is P over Q. I say that P over Q is equal to 0 mod 2 if P is even and Q is odd. Okay, that's what I mean by this kind of condition. Okay, so that's the theorem, and I want to do two things.
Excuse me, but
yes.
The determinant is positive here, determinant of nu?
No, it's a unitary transformation.
Yeah.
So it's
So like any square root?
No, yes. It's a complex number of absolute value 1.
Okay, but which square root do you take?
But there is this kappa. There is this kappa. So for some kappa square, kappa 4, so it doesn't matter.
Sorry.
No, it's nice. Thank you for asking. And you will. That's a very important question. Very important question, because you have seen in the proposition I've given, I don't have a kappa. I have square root of a plus I square root of b. Okay. So this means in the proof I will have to follow this square root of determinant. So, but you know, when in the theory of theta function we do that a lot. Like, and this is exactly what I'm doing. Thank you. So what's my aim now? No. I have 20 minutes left? 30. 30, thank you. Yeah, 7/16, it's okay. Okay, so I want to do two things. First thing, I want to explain why this theorem implies the two proposition and even another one. And what's the difficulty? The difficulty is that these statements are about a cyclic group. And here I have a construction with higher dimensional Abelian varieties. And my group G, you see, it has no reason to be cyclic. So you have to find the Abelian varieties, you have to find the unitary transformation, such that this quotient is a cyclic group, and simultaneously you have to adjust it so that you have this congruence property. So it's a kind of gymnastic, I don't know. So let me explain to you how I do it for proposition 1. So I have rewritten the theorem, okay? And how do I prove that square root of A plus I square root of B is D-critical? So I have to choose one elliptic curve. I will take n equal 1. So the elliptic curve, I will give you here the lattice. I square root of AB over 2Z. And I give you what is the nu. Nu will be 1 plus IT over 1 minus IT for this value of t, square root of B over A. So it does not, nu does not preserve this lattice exactly. It's commensurated. So how do I apply this formula? You see A plus B is D. So I have square root of D here. And here I have the square root of something which is square root of A plus I square root of B over square root of A minus I square root of B. So you multiply the denominator by the conjugate value. You get a square on the numerator. And you get D at the denominator. And this is why when you apply this formula to this nu, you get exactly square root of A plus I square root of B. And then you have to determine the sign. But I will explain later how you determine the sign, but not this time. So this was kind of easy for elliptic curve. Okay. If I go to the second example, I have to find my Abelian surface. And here is my lattice. So it looks a little bit complicated. But the point is that this lattice is related to, so in this case, the Abelian variety will be a CM Abelian variety associated to a CM field. This CM field will be the field generated by IT. T is exactly this number. And lambda is not exactly the ring of integer. It's not even an ideal here. It's something in between. You have to cook. So I cooked this because I knew the computer told me that the value I had, square root of A plus this, was critical. Because I will never have the energy to cook this example if I did not know. I mean, I will be able to get this critical value because it's not an ideal. It's okay. Okay, so you don't see a lot. This is why I want to explain to you proposition 3. Well, maybe it will be less general, but you will see more the theory there. So in this theorem, I need an Abelian variety with. So one point is which is very important is that it's principally polarized. So you don't take any one in the when you change lambda, you have to keep the fact that it is principally polarized. And one point about this theorem is that in the Q endomorphism, I just asked for the existence of one unitary transformation. But for sure, I can restrict myself to the case where you are CM. A lot of Q endomorphism. So this is my proposition 3 now. I need some notation. So, you know, to construct CM abelian varieties, you start with a CM number field, which is a totally imaginary quadratic extension of a totally real number field. And you, yes?
So what is the function f for this critical value that you just gave?
I will give later on. I will give. That's the proof. In the proof, so as I said, my theorem will have maybe 4 different kind of equivalent forms. I have given one, and I will give more precise where I give what is theta. So the degree of this extension is 2n, and I also choose a CM type, which means that since it's a number field of degree 2n, it has 2n embedding into C, but they came by pair of conjugated 1, so I choose 1 in each pair, and this is called the CM type. And so this allows to define the reflex norm, which is a product of the image of mu by all the embedding chosen by this CM type. So it's just half of the usual norm, and the usual norm is the square of the absolute value of the reflex norm. Okay. And then in this setting, you have this very nice formulation. If you, for instance, choose for K the cyclotomic field, or if you assume that K is ramified at a finite place over its real point, then, so this is some assumption. I can remove this assumption, but I want the statement to be simple. So just and take an element S in OK, an integer in this, and consider mu, which is 1 plus some imaginary element of the form S minus S bar. So it's slightly more general than being the double of imaginary integer. It's just S minus S bar. And then always the reflex norm is critical on this group, which is the integer divided by mu OK. So, and as you know, it's very easy when you have a mu to detect what is the structure of this abelian group, because you just have to look how it splits, and so it's easy to choose some mu for which this is really cyclic group. And so this is, for me, kind of reformulation of the main theorem in a special case, but it's kind of general. And so reflex norm, so you can say reflex norm of this guy, 1 plus some imaginary, 2 times imaginary integer are always critical. Up to sign, there is a sign here.
But what do you mean by K over K inter R ramified? Ramified where?
At finite place.
Sorry?
At finite place. Only at finite place.
At some finite place.
There is some finite place at which K, yeah, because it's ramified at infinity for sure.
Yes, of course.
So, but so ramified means there is some finite place at which it is ramified. This is what, and in case it is not ramified, the statement is there exists some CM type for which n phi of mu is critical. Okay. What is L? L is an integer, and I think I forgot. I think any integer, not at least starting from 5, and maybe say odd integer. Okay, to be safe. So let me now give an application where I take S to be just e to the 2I pi L. And so this is my example. If I take S to be e to the 2I pi L, when I'm writing S minus S bar, I get a 2I sine k pi over L. Okay. Okay. And when I assume L to be prime, here I'm assuming L to be prime, and it's nice to assume L to be prime because the quotient group then will become cyclic. So, and then I know that in fact in this case you get that lambda is critical. This value is a critical value for some integer d, and you can compute d as the Lucas number, which is the sum of the Fibonacci at L-1 plus the Fibonacci number at L+1. So you have this nice example of critical value as byproduct of this proposition on very general CM field when you apply it to the cyclotomic field. Okay. And so you see there is this assumption that Laurent asked me about. This is this assumption on the first line about ramification or being cyclotomic. And how is it used? It's used because it implies the existence of an ideal M in the ring of integer for which the Abelian variety that the CM Abelian variety that you construct with this CM number field and with this ideal is in fact principally polarized. And I remember I really wanted to have a principally polarized Abelian variety. I will explain to you later why. And I thought the answer was no. There is no way to manage to be principally polarized. And I asked Emmanuel, and he told me, just look, this paper of Shimura. So, thank you. No, but I mean, if not, I cannot prove anything. I mean, if it is not principally polarized, I cannot prove anything for this proposition 3. I mean, okay? For this, yeah. And how do you see that the theorem implies a proposition 3? Why does so? Now we know that it's principally polarized. You just have to compute the square root of the dimension. What you have to compute, the lambda will be the square root of this dimension by the determinant of nu. But the dimension is the norm of mu, because the group is OK divided by mu OK, so the cardinality of this group is the norm. And the norm is the product of the reflex norm by its complex conjugate. And on the right-hand side, you have the reflex norm of nu. You have the determinant of nu. The determinant of nu on C is just the reflex norm of nu. But nu, I will choose nu to be mu over mu bar. So this is the ratio of the reflex norm of mu over its complex conjugate. So it's cancelled. You get a square. And but the formula I have for in my theorem is the square root of that. So then you get that the reflex norm is a critical value. So that's the way theorem implies proposition 3. So now we want to understand the theorem. And this is what I plan to explain now. And what are the function? What will be the critical function associated to my critical value? And how I prove these functions are critical. So the function will be theta functions. So let me recall the definition of theta functions. So I have my Abelian variety, my principally polarized Abelian variety. So I can write it as Tn over a lattice. This lattice, I can choose one part to be Zn, but there is it's a rank 2n lattice. So there is some other part which is the image of Zn by a complex matrix, and by Riemann, by a theorem of Riemann. This matrix has to satisfy some condition to live in the Siegel upper space, and which is it has to be symmetric, a complex matrix which is symmetric, and its imaginary part, which has to be a positive definite a real quadratic form. And on this Siegel upper space, the symplectic group act by this very classical formula, alpha tau plus beta over multiplied on the right by gamma tau plus delta. And now I give you the functions, the theta functions. So theta functions, they are not exactly functions that live on the Abelian variety. They are periodic in Zn. So they are periodic in Zn. So this is why you can develop them in Fourier series. So the Fourier series is here. Here it's so it's higher dimensional. I'm writing transpose mz. Z is a n vector. M is a n integer. And so transpose mz means the sum of mi zi. And the Fourier coefficient of this series are Gaussian. And the matrix that controls this Gaussian is this tau. And since it has a positive imaginary part, and you have a I here, so this series converge. And those are the theta series. And those are exactly the object that you need to prove that this complex manifold is in fact algebraic manifold. It's projective. That's the way you prove it, by introducing this theta function. So I have this theta function, periodic in Zn, and not exactly, but semi-periodic in this direction tau Zn. And what will be important later on is how they depend on tau. The point is that when I'm given this Abelian variety, I don't know tau. I just know tau up to Spn z. But I have to choose tau. To know the theta function, I have to tell you what is my Abelian variety, but which tau do I choose? And so it will be important to understand how tau changes when you let the symplectic group act. So the formula are particularly simple for a smaller group, which is the Igusa subgroups that I introduce now. So you are among the integral symplectic matrices, and you just look at those which are equal to 1 mod 2, and which still satisfy this condition that the diagonal part of beta and the diagonal part of gamma are in fact equal to 0 mod 4. Okay, this is so-called the Igusa subgroup. Okay, and so now what is the reformulation of my theorem above? It's a more precise statement, and maybe less easy to grasp, but it's more precise. So I fix tau in the Siegel upper space, and I'm assuming there is a guy, a sigma, in the Igusa subgroup, which, when I act on tau, it almost preserves tau. It changes tau by some kind of change of basis given by some matrix with integer coefficient. So it's sigma tau is transpose d tau d. So this is this assumption, strange assumption I have. Okay, I agree. And then under this assumption, I can introduce this group G, d minus 1 Zn over Zn, which is some kind of part of the torsion group of the corresponding Abelian variety. And then the statement is that all the translate by an element Z of the theta function, all the translate, if you look at them as function on G, they are lambda critical for this critical value, a determinant of gamma tau bar plus delta square root. Okay. So this is the key lemma. Okay. So the first thing, you see, I'm progressing in the proof when I'm writing this lemma. The first thing you have to understand is this strange assumption here. How do you get it? First, how do you get it from my assumption I had on that nu is unitary? Okay, and in fact, the existence of this tau and sigma satisfying this condition will follow from the existence of this unitary nu, because the fact that nu is unitary is the fact that the holonomy h nu is symplectic with a rational coefficient. So, but you know, if you have a matrix, with a rational coefficient, you can always write it as a product k a k. Matrix with integer coefficient, diagonal matrix, matrix with integer coefficient. And so there is a version over for the symplectic group, which is due to Shimura, and which tells you that any matrix with rational coefficient you can write as a product like that of matrix with integer and a diagonal matrix with integer coefficient here. And there is d minus 1 here. And so there is no transpose because it's diagonal, but transpose is OK. And there is another matrix here with integer coefficient. So, and then you play with that, and with your matrix nu, and then you get your tau, and this relation sigma tau is transpose d tau d. I don't write the detail, okay. But you have transformed the fact that nu is unitary by the fact that you have been able to choose the parameter tau in the Siegel upper space such that sigma tau is transpose d tau d. That's the key point. And it's not easy to find the tau even when you know the Abelian variety. So let me give you an example. Lambda is 2 plus I square root of 7. So I told you the elliptic curve is z, it corresponds to the lattice z of I square root of 7. Okay, sure. But what is the tau? The tau is not so easy. The tau is minus 31 plus I square root of 7 over 121. And because it has to satisfy, I have to be able, this number has the property that I am able to find an element of SL2Z which is equal to 1 mod 4, and such that when I apply sigma to tau, it's d square, and so 121 times tau. Okay, that's the remark. I am going on. I have 5 minutes left. Okay, 4 talks, 4 slides. That's okay. I want to tell you about the proof, because we want where does all this enter into the proof. So what is nice into the proof is that it uses only classical tools that you have in a textbook on Abelian varieties. So if you open a textbook in Abelian varieties, you learn 3 formulas. Okay. And I use these three formulas. So what I want to prove that this theta function is critical here. This theta function is here, and critical means exactly this condition. So first I want a formula for what is here, theta tau z plus w, theta tau z minus w. So this is the addition formula, which is due to Riemann, and which tells you that you can write it as a sum of function of w, function of z, and this function of w and function of z are just some other kind of theta function. So it's a very easy way. It's very easy to check this equality. You just expand, but it's nice to have it. So and then you see, I will plug this equality here in here. So I will sum over w. So I want to sum this over w. And there is another formula in my book to sum this over w. This is called the isogeny formula. So that's nice. The isogeny formula tells you that if I'm averaging this theta function over this group of torsion points, I get another theta function, but computed at a slightly different tau, which is transpose d tau d. Wow, exactly the one I had. And I know that this one is, this is my assumption. Transpose d tau d is the image of tau by sigma. Now, what I want to check is that theta xi of 0 transpose d tau d is just proportional to theta xi of tau. This is what I want, exactly, but with a coefficient which does not depend on xi, because there is a sum over xi, so it will be, you will have this, you want to have this for each of them. And so I open my textbook, and I have a transformation formula, which tells me that the way the function theta xi transform does not depend on xi. There are sections of the same line bundle. And the multiplier is this determinant. So I think this ends the proof. And I have 2 minutes left. Okay. I will ask you 3 questions. Something I cannot do, but which are statements which are completely elementary. I noticed that when you choose in the computer experiment, all the values I have constructed are Weil number. They have absolute value square root of d, and all their Galois conjugate have absolute value square root of d. Okay. For a while, I thought it's always the case that they are Weil number, but I pushed my computer experiment that it's not the case. So, but I noticed that always when d is prime, sorry, wow, I'm too efficient. I noticed that when d is prime, lambda and d over lambda are always Galois conjugate, except for lambda is 1 and lambda is d. And you have to assume d prime because when lambda 1 is d1 critical, and if d is md1, then lambda 1 will be also d critical because you make it not depend on the other, on the new variable. So you have to restrict to d prime. So I don't know why this is whether it's correct or not. Another thing, so now I'm going to the second question, which is even simpler. It's about my proposition 1. And the proposition 1 looks very much like this question 2. Proposition 1 was telling us that always when A plus B is D and under this congruence condition, square root of A plus I square root of B is D critical. This was my proposition. It's always D critical. And we notice that the set of D critical value is invariant by Galois conjugation. So then you deduce that minus square root of A minus I square root of B is also D critical, okay? Except that minus square root of A is a Galois conjugate of square root of A if A is not a square. So there are cases where A is a square. So for instance, if you look at the value minus 1 minus 2i, it is not 5 critical. If you look at the value minus 2 minus I square root of 7, it is not 11 critical. So the construction with the theta function gives always a plus sign. Because I had the kappa in the statement, but then you work harder and you see that the sign is plus. It's like in the Gauss sum. In the Gauss sum, the sign is a plus sign, and here the sign is a plus sign. But when you do a computer experiment, you notice that when D is not 2 mod 3, always minus square root of A minus I square root of B is also D critical. But I have no proof of that. Okay. And the last question is even more ashamed about it. Is whether if you take D to be a square, whether I know M is M square critical, but I don't know whether minus M is M square critical. So for computer experiment, you can see that minus 3 is not, minus 5 is, but for minus 7, I don't know. And the final challenge is, can you do the proof I have done without using elliptic curves? Is there a way to, because it's an elementary question. I mean, square root of A plus I square root of B is a critical value. It's an elementary question, so maybe there is a proof without using elliptic curve. I don't see how, so it's a final challenge. And happy birthday.
Thank you very much. Are there any questions?
Can you explain a bit how your program works? Because surely you're not just testing random functions and.
So there is a very efficient implementation of Gröbner bases, and and then for D equal 11, I just use this, which is on you find on Maple or Mathematica, and it gives you all the solution. But you see, so it's constructed to solve any system of polynomial equation in many variables. And here I'm kind of dealing with 11 variables, degree 2, and I'm very surprised it works. I mean, but that's incredible. But then when you go to 13, it doesn't work anymore. I mean, so starting when I said I have done 13, 15, 17, so then you use something else. What you do is you start with approximate solution, and you do Newton method, and you get a lot of example, and you wait, and then because you know something that the computer does not know. What you know that the computer does not know is that the set of solution is invariant by Galois. So when you get a lambda, and so you can do the product of the x minus lambda, all the lambda you get, and you get a polynomial, and at the end it has to have integer coefficient. So when you get this polynomial as integer coefficient, maybe it's not a proof, but you have some kind of feeling that maybe you have all the solution. You have no proof, but that's the way we.
Can you give this list for 11 again?
Sorry?
Can you show again?
Yes. Yes. What happens is. Whoa. Well, it was there. Sorry, I'm too fast.
So like now 4 plus square root 5 is not in the theorems that you have. This is like
no, I don't get 4 plus square root of 5 in my theorem. Yeah. I don't. The theorem does not give. The theorem does not give 1. The theorem does not give. The theorem just gives numbers which are Weil number. Here you see all these numbers are Weil number. Starting from the 3 last are Weil number. The 3 first are not. Yeah. I mean, at least what? No, I mean this one is not. Yeah.
And so the first 2 are easy to get, and the 4 plus square root of 5.
Sorry, the first.
The first 2 lambda are easy. Well, that you said you had the code.
Yeah, I mean the first 2. This one are kind of trivial. This is the function is a Dirac mass at 0. This is the constant function. This one is a function which has some value at 0 and a constant value outside 0. The third one, yeah. This is given by the third one was given by the example 3 in my previous slide.
And I square root 11 is
yeah, it is this one. This one.
Okay.
Even for 11, are you sure that you have no other?
Yeah, there's the Grobner basis.
Okay.
A Grobner basis, it takes the ideal of equation, and it gives you the ideal. It gives you the generator of this ideal in a specific order, in such a way that at the very end, you have less and less variable, and at the very end it depends only on the variable lambda, and you have a nice polynomial in lambda, okay, huge degree, and you ask him factorize, okay, and it begins lambda minus 1, lambda minus 11, lambda and so on, and then you
Up to 19, it's okay, not even.
No, what happens, what I'm saying is that for 11 I apply Grobner. For other, after I apply some random choice of solution, looking at going through Newton method. Boom. What's the point? I mean, I think if you look at the list for, if you look at what I'm saying, if you look at the list for 13, 15, there are numbers that I don't understand, so I should already focus. And here even what I've shown, like minus square root of 3, minus square root of a plus minus square root of b. This question I asked the question 2 about, which is a very simple algebraic number when a is a square. When d is equal to 2 mod 3, so when d is not equal to 2 mod 3, so let's, for instance, what will be like I think 15, like 15, and I can see that the computer gives me, you see, this is this question at the end. This question 2 here. Even for d equal 15, I have a list of, I will have a value which will be, for 15 it will be minus 2 minus I square root of 11. I don't know what is the corresponding function. I don't have a clear answer to that.
I think maybe any more questions?
Sorry, can he tell us what those pictures were? What?
Ah, thank you. This is about Emmanuel. So this is the exercise. Who has solved the exercise? So this is for sure Emmanuel, Laurent, and he, Eke points. So what we have here, you start with the square lattice inside R2, so Z2 inside R2, and you take an integer. Here I have taken the integer 3061, which is a prime number, and you take all the lattices of index 3061. There are 3062 such lattices, okay? And so these lattices have same volume, which is 3061. So you renormalize them so that they have volume 1. So you get element in SL2R over SL2Z. So this is SL2R over SL2Z is a space of dimension 3. So you have 3 coordinates. One coordinate is x, y, which correspond to the point in the upper half space, okay? But it's modulo SL2Z, so you can put it in usually in this part of the upper half space. Here. For the measure dx dy over y square, okay? And what you notice, if you replace y by 1 over y, the measure becomes dx dy, the Lebesgue measure. So this is why I have drawn the picture in coordinate x 1 over I. So the image of this is this, okay? And simultaneously, I have the component in k. So I call it A. A is a number between 0 and 2 pi, this A. And so those are, I have not shown you, maybe I could have shown the thing in dimension 3, okay? Maybe I should have done this picture. I was not able at that time, but nowadays maybe it's easier. Because I did that more than 15 years ago. This picture before I knew you. And you see they equidistribute according to the Lebesgue measure.
What are the red and the blue?
Probably it's not so important, but I gave a list, this lattice as a list. And I like when I'm doing some kind of a list, and instead of drawing points, which are all of them are black, I add a small parameter which changes the color continuously from the beginning of the list to the end of the list. So maybe that's when your lattice is moving, your color is moving.
Thank you again.
Thank you.